Assalamu alaikum warahmatullahi wabarakatuh. Dear students, in this session I'm discussing the issue of autocorrelation regression model. So if you remember, we have just started with the classical linear regression model assumption in our previous sessions. And there we have covered the issue of heteroscedasticity and also the issue of endogeneity. But now I'm just simply discussing the problem in the issue of autocorrelation. How the autocorrelation can be a serious problem in regression analysis, dear students. According to the classical linear regression model assumptions, or you can say according to the Gauss-Markov assumptions, there are certain conditions in assumptions. If they are simply met, then you can say the model is blue. The ordinary least square method is just blue. By the blue, we mean it's best linear unbiased system error. So among those assumptions, one assumption is that there should be no autocorrelation. So once again, I'm just repeating. Among the classical linear regression model assumptions, one is just there should be no autocorrelations. So what do we really mean by this? If you have a model, right? So in our model, the error term must not be correlated with itself technically. So you can say the covariance of the error term in one period and the error term in another period must be zero, right? So for more clarity, I have a model today, and this is the multiple linear regression model. For my analysis, I have a set of independent variables such as the government expenditure, exports, and investment. And I'm just trying to figure out whether these independent variables, they are just affecting the GDP or not. But before exploring this relationship, it's really important for me just to know how the error term is just related. So if there is autocorrelation by the auto V mean response, if this error term is just correlated with its own value, then it means the model is just suffering from the issue or from the disease of autocorrelation. In that situation, the model is just not blue. And by the blue, we mean best, right? Linear and unbiased system error. So you can say these coefficients are these estimations we have, such as beta naught, beta 1, and beta 2. They are not true. They are just not truly representing their population counterpart if there is autocorrelation. As simply you can say the relationship between the x and y that is just not trusted in that situation. So you can say the covariance here, right? This is just the technical formula. You can say the covariance of the error term at time t and the error term at time t minus 1 must be 0. Okay, dear students, since this is just the issue in the problem, you can, this is a disease for the model, right? And before detecting this disease in the problem, right, inshallah, I'm just briefly explaining how first the error term is just causing the solid issues for the model, right? And after that, inshallah, I'll learn how the Durbin-Watson test is used for detecting this error. Okay, in our previous sessions, if you remember, I have covered the issue of heteroscedasticity, and you have learned that it's just causing issues for OLS. So what are the problem does autocorrelation uses or causes in OLS? So number one, it is just inefficient estimates. What do we mean by this, dear students? As you know, I've just explained multiple times that the function of the OLS is just estimating the beta 1, the coefficient, you can say the estimators we have, right? So for example, this beta 1, beta 2, all of them, they are just estimates. So these estimations, they are not efficient in case of the autocorrelation. What do we mean by efficient? It means the variance is just high. And once the variance is high, you can say it's not certain, right? It's not precise. So once the variance is high, there is also another issue of the standard error. Then you can say the standard error is also not valid. Why? Because the standard error in that situation is either overestimated or underestimated. And you know the t statistic and the f statistic, they are also just depending on the standard error. If you remember, I've just explained that the formula of the t statistic is simply equal to the beta 1 hat, right? Should be divided by the standard error of the beta 1 hat. So now, if the standard error overestimated response, by the overestimation means that it's just higher from its actual value, right? Then you can say the t value is just deflated. And if the standard error is just underestimated, the t value is just inflated, right? The t value is just not reliable. And once the t value is not reliable, you know that the p value or the critical region is also just depending on the t value with the confidence interval. That is just depending on the standard error, that is just also not true. And also the model diagnostic, you can say the model is also misspecified. You can say there are some true independent variables, they are just missing because of the autocorrelation. So dear students, these are just problem, and I've explained them in our previous sessions in detail. Right, so I'm not just repeating again in much detail, right? So these are just the problem they are just caused by the autocorrelation resistance. Okay, now you are learning how we can detect the autocorrelation issue resistance using both the Excel and Stata. Right? So I'm just opening my Stata file. In Stata, you just click on the file, click on import, because I'm importing my file from the Excel spreadsheet, because the data is stored in the Excel file. Click on browse, and I have a special file by the name of autocorrelation Stata file, and just click on the import first row as a variable name. Okay. Okay, this is the GDP here. You say this is our dependent variable, government expenditure, export investment. They are independent variable, and this is just not relevant. I'm dropping it. Okay. Okay, one thing you should just learn that the autocorrelation issue is just common in the time series data, and by time series data we mean the data and the variable they are just collected on different points in time in we have such as here. Okay, for example, if this is just representing year, so in the year one the GDP is this much amount, right? And this in year two this is GDP. So all these variables, the data and the variable, they are just collected across different points in time we have. Similarly, for the government expenditure, exports, and investment. So if you have a data set such as like this one, right, then it is just called the time series data set, or the time series database. In this situation, in Stata, so you should define your time variable. Why? Because if you do not define the time variable, the Stata does not know what is the time variable. So here the time variable is just year. So we have a special command, and that is just you should type TSSET, right? And then just select your time variable, right? And just press enter. Okay, now the time variable is set. Now we are just running the regression, and for regression you should type reg or regress, both of them are there, right? Okay, so first you should just put your dependent variable and then your independent variable. This is you should learn the Stata. When you just run regression, the first should always be the dependent variable, right? In all of them, and then you should put your independent variable. So this is the same regression output we have several times generated in Excel registers. Now we are just learning in the Stata. So the if statistic value is just less than 0.05, so you can say the model is significant overall. And for the individual significant, just look all these significant, all these variables, they are just positive, and also they are significant. You can say the government expenditure, exports, investment, they are just positively and significantly affecting the GDP, right? So for example, this is a coefficient of exports. How this is interpreted, you can say a unit dollar increase in exports, you can say just leading to 0.82 unit dollar increase in GDP, simply, right? And this relationship is just significant. But keep in mind, dear students, this output is not reliable for our analysis or for our research cases unless we are sure about the autocorrelation or some other assumptions. But now we are just talking about the autocorrelation. Okay, so before I'm just teaching you the method of Durbin-Watson, how to find out and how to detect the error of autocorrelation here. First, I'm just giving you the concept in Excel, right? Okay, in Excel, we are just using this function manually. In these functions, we have ET. This is the error term resistance, and for the error, you should just minus the one lag value, which is ET minus 1, and just this, it's the sum of the square value should be divided by the square value of ET. Okay, simply how you can find out these values. So the first you should find out the UT, which is error term. And you need to understand the error term is just computed when you subtract the Y value from the Y predicted. And for that, you should just run the regression and take the intercept value, the beta 1 and beta 2 from the regression output and find out the UT. So this is really time consuming, right? And I've just done this in our previous session. So I'm just taking the UT value or the error term directly from the Stata, and I'm also teaching you learn how you can find out the UT directly here. So UT address, and this is the error term. So in Excel, if you just predict the error term, you should just type predict, and I need the UT, which is the error term here for me, and then comma, and you should write residual. Residual means residual. This is just generate residual for me. So one more variable generated in the dash should just check here, dear students. This is another variable, right? And this is a long process in Excel, but the Stata is just computing so fastly. I'm just copying this variable and just bring it back here in the Stata. So dear students, here I have just simply brought the UT from the Stata, okay? I'm not just computing here. So I assume you know what is the UT or the error term. Now in this function, dear students, from the error term, you should just minus one lag value. So this is the point of concern for us, dear students, that this UT or the error term must not be correlated with itself. So practically you can say like this. For example, the error time in 2002, if these are the years starting from 2001, so in the error time in 2002 is should not be predicted by the error time in 2001, and the error of the 2003 should not be predicted by the error of 2002 in this way, right? So if you just try to check this relationship, you should just find out the one leg ut minus 1, right? 1 year before, one time before, simply, right? So just copy this variable, right? And just you should just paste it here one step down, just leave one cell just blank right here. Okay, when you paste it, you say this is just ut minus 1, ut minus 1. Now also you can find out ut minus 2. It means the autocorrelation does not mean that there should be no autocorrelation between ut and ut minus 1. There should be no autocorrelation between ut and ut minus 2, ut minus 3, ut minus 4, right? So if it is just one leg, two leg, so this is just the condition for all the students. Okay, if you just try to find out the ut minus 2, so how to find out? Then you should move this column 2 step down, right? Why? Because you are just checking how it is just related with the value of 2 period before. Okay, so here the interpretation, you can say the error term in the 2003 should not be predicted by 2 year before error term, which is this one, right? In the error term in 2004 should not be predicted by 2 year before. The 2 year before is just this value. So in this situation, you can say this is just the error term for the ut minus 2. Now I'm just interested to know whether the ut and the ut minus 1, they are just correlated or not. Okay, in this situation, in the numerator, the ut is just given. This is the error term we have, and this value is also just given. So just to find out the difference between these two columns simply, and for the difference you should just use this. Okay, now how to find out the difference? Equal sign from each value of the ut, you should just subtract one leg value, right? And just drag this down here, so simply. Okay, now you should just square this value, and for squaring this value, you know, I've taught you the function. You can just use the power function, power, and just take this value and just square it here. So this is the square value, you just drag it down. Okay, now dear students, we have this value in the numerator, and just you should sum it, and we need the ut square. It means the ut square value is also just needed. So ut square value, simply just take this value. This is the ut value, simply, right? And I'm just squaring this value. So clear. Okay, just this value, and you should multiply this with itself, and you can also use the power function, right? Okay, just drag it down here. So now we have two values, the value of the numerator and the denominator. Both of them are just given. So this is just the value of the, here you can see, students, simply this is the value of the numerator. Just you should take the sum of this value, right? And also you should take the sum of the value of the denominator, right? This is the value of the denominator, right? Now when for the test of the Durbin-Watson, this numerator value should be divided by the denominator. Okay, simply we found out the Durbin-Watson value is 0.337. Okay, what is the d value? We can say the Durbin-Watson value is 0.337. Now what is the interpretation, dear students? Okay, just learn here. Okay, the interpretation is very much simple, dear students. The Durbin-Watson value we have just computed. The Durbin-Watson, that is 0.337, right? Okay, we have the Durbin-Watson test decision rule, right? And that is just, this is the criteria. First, you should learn that in a Durbin-Watson we have two limits. What is the Durbin-Watson lower limit and upper limit, right? So when you just find out the Durbin-Watson value, then the other information you need for the analysis here, just to learn how to know whether there is autocorrelation or not autocorrelations, you should know, right, how many variable you have. So from the standard, you just can take here, just look here, the total observation, number of observations we have in the standard, there are just 55 observations, right? And the number of independent variables, dear students, we have, that is simply 3 independent variables. These are 3. Okay, so you can say the number of observation, which is n, we know that is 55, right? And you can say the k, the number of independent variables, we have 3, and the significance level we are just interested 0.05, the significance level. So we have a special table for the Durbin-Watson, and you just go there and check within the n and k, right, for the significance 0.05, the value of the Durbin-Watson, what is its lower limit and what is its upper limit. And this, the lower and upper limit should be taken from the table there. Okay, so I'm just checking the value. So this is the special table, dear students, of the Durbin-Watson significance table. And just come down, we should just check, this is just for the significance of one person, and this is just for the significance of the 5% user. So now for the variable of 50%, we have many variables. So the n, okay, sorry, so for you should just search for the n50. So the n50 is just simply here, this is 50. For example, 55, this is our observations. You can say, look here, this is how much we have. This is 55. So for the n55 here, this is n55. So this is these two columns, this is just for 1k, and another two columns, they are just for 2k, and this is just for 3k. So you can say for 3k, dear students, we have 1.45 and 1.681, 1.452, 1.681. Okay, so 1.452, 1.452, and 1.681, right? 1.681, dear students. Okay, this is just, you can say, the lower limit, and this is the upper limit we have just taken from the table, right? Now, when you have lower and upper limit, dear students, right, then you should find out these values also. And you need these four values. Okay, so we found out the lower limit. This is our lower limit simply, and simply this is our higher limit. You can say, right, dear students, and this is the 4 minus du. So from the 4 you should just minus the du value. This is the upper limit value, and from the 4 you should minus the lower limit value. Right? Sorry. From the 4 you should minus the lower limit value. Now you, once again, what's the problem? Equal sign 4 minus this value, right? Lower limit. Okay. Now this is just the decision rule criteria. Keep in mind, dear students, in the Durbin-Watson we have three main values, right? The first is, this is the lower limit, and this is just a higher limit. Okay, just 0 is indicating there is perfect positive autocorrelation, and 4 is just indicating there is perfect negative autocorrelation, right? And these two values, this is the central value, right? So now we have some sections here, you can say some intervals we have. So according to this rule, dear students, if the Durbin-Watson value just lie in this range, it means that is just lower from the Durbin lower limit, right? You can see it's perfect autocorrelation. You can say perfect positive autocorrelation. And if the Durbin-Watson value is just lying in this range, dear students, between the 4 minus dl and 4, right, then you can say they are perfect negative correlations. You have learned how you can find out these two values. Once you just take these two values from the table, then you can find out these four values, right? Now, how you can compare, if just it is in this interval, you can say there is positive autocorrelation, and if it is in this interval, there is positive negative autocorrelation, right? And keep in mind, dear students, if the value of the Durbin-Watson is just between the dl and du here, you can say the result is inconclusive. You cannot say whether there is autocorrelation or not. And also, if it is just here, then it is inconclusive, dear students, right? And simply, dear students, the result is just significant, or you can say there is no autocorrelation only if the values just lie in this range, right? It is just between the du and 4 minus du. So how much is the value of du? This is 1.681, and this is 4 minus du value. So the value of the Durbin-Watson, which is 0.337, dear students, it is just lower from this value, from 1.421, right? Lower from this Durbin lower limit. It means just lying here, dear students. In this situation, you can say there is positive autocorrelation issue we have in the model, right? So now, based on the Durbin-Watson test, we are just concluding there is the issue of autocorrelation, dear students, in the model. Now, how you can find out the Durbin-Watson value in this data? Simply, dear students, it's so simple. Once you have the regression output, then just you should write dw state, right? This is Durbin-Watson. And the value here, this is 0.337, and this is the same value we have, dear students, which is 0.337 here, right? And once you have this Durbin-Watson value, then you should just compare it in the significance table, find out the dl and the du, and then just decide whether the autocorrelation is there or not, dear students. Okay, so now according to the Durbin-Watson test, there is a serious issue of autocorrelation we have, and that is the positive autocorrelation, dear students. Now, what are the solutions? What are the solutions for this? How we can solve if there is the issue of autocorrelation? So there are a number of issues. I'm just briefly telling you how to remove these issue, right? Okay, the issue of the autocorrelation here, dear students, we have the a number of issues you can use. So you can use this, the Nuvi West test. This is a special test which is correcting the issue of autocorrelation. Okay, so now I'm just running the Nuvi West test. Okay, how you can run this test? Very much simply, dear students. If there is a positive or negative autocorrelation, then you should just type Nuvi, N-E-W-E-Y, and then you should just put your dependent variables. Or dependent variable, this is GDP, and your independent variable, simply, right? And then you should just put comma, and after the comma you should just type leg 1, because we are just checking for one leg value, right? And just press enter. Now the after this output is just reliable. Why? Because the Nuvi GDPR, you can say the Nuvi test, which is the name is just here. Okay, you can see this, call it the Nuvi West test, right? The Nuvi West test is just simply telling you that there is no autocorrelation. This output is just reliable, dear students. You can just interpret this value. Why? Because now we have corrected for the issue of autocorrelation. The only thing, dear students, just you should identify whether we have autocorrelation or not. Then simply removing the autocorrelation. There are many methods in test we have that is just removing the autocorrelations. So the Nuvi West is just adjust the standard error for the autocorrelation, and once the standard error is just adjusted, then you can say the issue of the autocorrelation is just removed. Okay, okay, we have many other methods also. We have also the method of first differencing. In the method of first differencing, that we are just find out the first difference of the GDP and the first difference of the government expenditure and exports and investments, and after that you are just running the regression of the first difference. What do we mean by the first difference? Means simply I'm just telling you about the first difference. Okay, for example, this is the data, and if you just find out the first difference, okay, I'm just explaining only one. Okay, for the first difference, okay, let me say if first difference for first difference value of GDP, for example, how you can find it out, right? So for the first difference, just from this value, from the current value, you're just subtracting the previous value. Only just you check the difference, and you just find out the difference for all the values. So this is, you can see the first difference of the GDP. So one method in solution is just you should find out the first difference of all these values and then just run the regression. So and instead of how you can find out the first difference, and just it is easy, dear students. You should generate the first difference column, dear students. And if you generate the first difference, I'm just giving you the name. So this is the name of GDP. I say the DGDP. This is the name of the first column, and then equal sign, and you should just write the D, right? Just type D dot and the GDP. This is just generating the first difference of the GDP. In similar way, you should just I'm just generating for the government, so you should type the D government expenditure, dear students, right? And just equal sign and D dot the government expenditure. This is the second variable, and also generate, dear students, the D investment. It means the first difference of the investment, and then you should just type the D investment, right? This is the method, dear students, you should learn. Okay, this is D investment. Okay, now I've generated two independent variable, right? One export is remaining, so you should just generate the D export by the first difference of exports, and this should be equal to D export. Now we have the first differences of all. Now just run one more regression, just regression, and this is our dependent variable for the first difference and the second first difference of all other independent variable, and just press enter. Now this output is also reliable, dear students, and this output just you can interpret it and use it for your analysis. So this is output, dear students, based for the first difference, dear students. what the first difference is just doing your sense, just eliminating the autocorrelation your sense. Okay, so you can use both method, this method, the Nuve best method, and also you can just use the first difference method. And one more method, dear students, we have that you just add the leg of the dependent variable to the model, and that is also just finding out, and that is solving the issue. For example, this is the GDPR dependent variable, and these three are independent variable. So find out the leg of the GDP. Leg means one leg value of the GDP, like we have for the error term, right? So just take the one previous value of the GDP. So if you just find out the leg of the GDP, this is also one method. You should generate one independent the leg value of the dependent variable. So the leg dependent variable name, I'm just giving a name, generate the leg, right, of the GDP, for example, and equals, and just you should type L.GDP. This is just creating the leg value of the GDP durations. Okay. Okay. Now, if you have the leg value of the GDP durations, look, we have the leg value GDP. Just sum the same regression. Okay. Look, I'm just running the same regression. Just these are dependent variable. These are independent variable, and among the independent variable, also just incorporate the leg GDP durations. So now this is another output. This output is also reliable. You can interpret the coefficient of government expenditure, exports, and investments. The leg GDP is just only for the purpose to observe the autocorrelation. This is only solving the issue of autocorrelation resistance. So this is also the output which is trusted, and you can use it in your analysis situations. Okay, one more method here I've mentioned, and that is just for the generalized least square method, right? So this Excel version is old, and this method is just not applied. Okay, so you can just use these method, the Nuve-based method, lag variable in the first difference in these methods in your analysis situation. So in these method, they are just removing the autocorrelation situation. Assalamu alaikum wa rahmatullahi wa barakatuh.